I was just counting the sixth talk in Talks Away series. It feels nice. I think you've reached already the sixth talk. And I'm very happy that today one of our colleagues, Dr. Asha Nair, who is going to talk about a very, very important topic of public health, public importance globally, and particularly in India. And I think biologist or non-biologist, everyone has heard about, and I both not, but maybe experienced the kind of brunt of the topic that she's going to talk about, and that is antimicrobial resistance. Unfortunately, I have seen some of the actual pathological reports of your relatives and others, where you can see that when they test certain bacteria infections for resistance, you see that it's resistant to many of the antibiotics that we typically use, in the clinic, and that's why this problem is so important. And again, I think you're happy that Dr. Asha is working on it and doing research and also trying to find some solutions for it. So I welcome Dr. Asha to talk about this topic, and then at the end we'll have some question and answers. Thank you.
Thank you, Saurabh. So, like Saurabh said, today I'll be talking a little bit on what is antimicrobial resistance, how it occurs, and what are the future directions with the help of which we can tackle this issue of public health. So, before I dive into the core of antimicrobial resistance, let's start with a story. So, we all have heard about Black Death, right? Plague, right, which caught hold of a majority of Asia and Europe during the 1300s, the mid of 1300s, where almost 30 to 70 population was killed. And the infection was so severe that if you touch the cloth of an infected person, you are infected. And a healthy person who goes to bed fine may never wake up in the morning. That was the severity of the infection during Black Death. But did that end by 1300? No. It kept on coming back through the next centuries. So it reached to a place where it is in 1600s. There was a small village in Britain called the village of Ia. So what happened there was it caught hold of the Black Death. So now what they did was they closed down the village. So they decided that they are not going to travel, because the moment they travel, they are going to spread the infection. So for the others, or for the global security, they decided to sacrifice their life. So that is considered as one of the most heroic acts of self-sacrifice by the people of the village of Yam in history of Britain. Okay, so here I'm saying the word they have self-contained themselves. So let's see. We heard the same term in 2020, right? We heard the same containment in 2020 March when our whole country was closed down. So what changed and what didn't change from 1300s to 2020, that we are still scared of the quarantine, still scared of those infections? Maybe just the microbes have changed. The Black Death was caused by a bacteria, whereas your COVID was caused by a virus. Why I brought in COVID is because everybody sitting here has gone through that. There is nobody alive at this point who hasn't gone through that problem of COVID, right? So we know how much we were scared. We closed down ourselves in the house, scared of something which we cannot see, right? So that shows how big they are, not in size, but their capability than what we are, right? So in 1300, what happened was that there was no medicine to use, and that's why they died. In 2020, what is that we are lacking? We are the most evolved species. We have every facility. Through the centuries, we had discoveries, inventions, we have everything. But still we have quarantine, still we have the pandemic, right? So what is that? In 1330, we had no medicine to use. Today we have every medicine to use. But are we actually just using them? No. We are using them, overusing them, misusing them to an extent that we are still stuck in the 1300s. right? It's not that we do not have the things or the facilities with us, but it's the way we are using it or misusing that has led to the COVID. So many of you will think, see, COVID didn't arise because of the resistance, right? COVID was just like any disease. It came and it killed. It has nothing to do with the resistance. But in COVID also, we had several waves. The first wave was primarily, the death rate was primarily because of COVID. But in the subsequent second and third wave, if you check, it's not directly the COVID. The COVID just made you weak, and it was just the bacterial infections that followed that killed most of the people. So it's mostly the secondary infection. And when you get into an ICU because of any disease, it's not just an infection, you might never come back is because of resistance. You go there, you just have a disease, but you never come back towards the people who are waiting outside is because of the evolution of the resistance. So what you have to know is it is waiting there to catch hold of you the moment you are weak. You have bacteria here in my hand, the things I am holding, even within me, right? Everybody knows we have bacteria within us. The good ones, bad ones, everything is there. Maybe I am even carrying some bad ones, but they are not attacking me because I am healthy. The moment I become weak, they will attack. So that is the way these resistance evolve. So here, now we have most of the issues is because of the evolution of resistance. And it has got a lot of role globally. So what I kept on saying resistance. So what is this resistance or how does that happen? Resistance is a condition in which a microorganism, be it a bacteria, fungi, or a virus, will become evolved to a stage that any drugs you use to kill them will not kill. Okay, so how does that happen? See, it happens naturally, but it will take millions of years for that to happen. But we probably is accelerating them. Why? See, I get a throat infection. How many of the people go to a hospital and meet a doctor? You just go to a pharmacy and get an antibiotic. Who told you to do that? It's up to you. You are self-medicating yourself. You don't know if the infection is a bacterial one or a viral one, but you're still getting an antibiotic, right? You go to any infection, doctors also prescribe what? Antibiotics. How many have heard about an antiviral being prescribed? Very rarely. Or an anti-parasitic drug. I don't even think anybody knows of an anti-parasitic drug, right? Until and unless you get a very specific disease. Otherwise, you go with a gut infection, chest infection, ear infection, nose infection, you are given antibiotic. And that's why bacteria have gained the momentum when you compare with viruses or any other microbes. Okay. And the reason, like I said, it is our misuse, right? I go to the pharmacy and I buy the antibiotic. So I am the one who is responsible for myself. Now you consider you have a cat or a dog, it fell sick. It is not going to the pharmacy and buying the antibiotic, right? You are only going and buying for that also. And you are actually misusing that by giving it. And you have agriculture where the plants are not doing anything to you. Still we are going and dumping the antibiotic onto its top. And you are flooding the whole ecosystem with the antibiotic. So you are pushing a normal bug to become a super bug. That is what we are doing. We are flooding it with so much of antibiotic that normally what should have happened in millions of years is happening in hundreds of years now. That push is coming from us. It's like a normal man became a superman. We are actually pushing the bug to become a super bug so that it can kill us. That is what we are doing. We are actually enabling them to kill us, right? So globally, why is it so much relevant? For WHO, from the last 10 to 15 years, this is a focus area, antimicrobial resistance. Why it is staying like that? Why its priority has never come down? First and foremost, as per 2021, the direct deaths that are caused by the resistant bacterial infections are 1.14 million. But if you look into the deaths which are contributed by resistance, it is 4 times more. What does that show you? Because in many places, if you are infected by COVID, your primary cause of death is COVID, but it is not what has killed you. So always antimicrobial resistance stands behind something and it will kill you. So you can probably never see that as the primary cause. Anywhere, finally, they will write the reason for death was COVID, because you got inside as you were infected of COVID, but you died because of probably the secondary infection of a pneumonia, which is caused by a bacteria. And that's why globally it is called the silent pandemic. It stays there and kills you. It's following you everywhere, but you don't know, or you can't see that, because it's always hidden behind something much bigger than the normal one. So now coming to India, the seventh biggest country with the biggest population in the world, we are under huge crisis, right? Because we have such a population which we can't even manage with. The facilities which now India have is very less than what our population is growing towards. So here, there is a report came from WHO in 2025, which is called the GLASS report. That is the Global Antimicrobial Resistance and Use Surveillance System. As per that, India is amongst the top countries which contribute towards AMR, where ideally amongst 3 of the bacterial infections, 1 is caused by a resistant pathogen. And I'm not going to the bacteria and depth of that, but mostly the notorious ones are called the escape pathogens globally. They are notorious. Most of the time you get an infection from these, which include the pseudomonas, which causes the pneumonia. You are infected, the chances of your getting cured by the currently available antibiotics is very, very less. And when you consider specifically India, we have very less data. How much ever we say, there is very less data that is coming from the rural areas, district hospitals or healthcare centers, where even when we say 1 amongst 3 is caused by the bacteria, I don't think so that is the real figure, because that's coming from the data. There is a lot, probably 70% of the data is not even coming where you can see what is actually happening. So I told you that we self-medicate ourselves, right? So if I'm going to a hospital and a doctor is prescribing me an antibiotic, ideally I should not have any problem. I should not be a target for the resistance, because I am following whatever I should follow, going, meeting a doctor, getting a prescription, following through whole antibiotics. So there is a study from few researchers from Stanford and Oxford, where their concept was, is the full course of antibiotics full of belleny? When I was in my schools, I remember doctors used to give you antibiotics for almost 7 days. Now it has come down to 5 days. And in some cases, they even give you 3 days. But where is that data? Who decides exactly how much of antibiotic you want? And it can change with each and every antibiotic. So how will you know? Maybe I get an infection, I got cured in 2 days. You might take it 8 days. So I am taking a course for 5 days, but I am fine by the end of 2nd day. So I am actually overusing the antibiotic, right? I don't know, because there is no system to check that. For that, you have to reach to a level of personalized medicine where each and every person's data and how much they will require to be on the precise level is needed. That's not there anywhere. No such studies. You only have generic studies which maximum tells you that this group of antibiotics require only 5 days. And it's purely a generic data, which we don't know. So even when you are taking a full course of antibiotics, probably you are overexposing your bacteria with the antibiotic. If that is happening, your microbes that is in your gut, which are the happy ones, they are becoming resistant. You don't know. Tomorrow, if they become resistant, the ones which are good can become pathogenic also. So you are overexposing your own body to the antibiotics. So there are infections and there are treatments. So if you have an infection and if there is a treatment and you get cured of that infection, it's fine to a great extent. But some infections never ever heal. Especially if you are a diabetic person, you got an infection, what are the chances that the infection is going to get cured? If your immune system is so down, what are the chances that you are getting cured? There are some infections which are never healing, and this happens because of antimicrobial resistance. So as I told, during the Black Death, there were no medicine. And the first antibiotic was invented by Sir Alexander Fleming in 1928. That's penicillin, which is produced by a fungi, and it is an antibacterial. It kills a bacteria. So in his Nobel Prize speech, he told, I did not invent penicillin. Nature did that. I only discovered it by accident. By that he meant the cure is always there in nature. It's just that we are unable to find it. So it's always there. He never invented that. It was there in the nature which he discovered. And again, during 1928 itself, he told one more thing. There will come a stage where penicillin can be bought by anyone in the shop. And if that happens, it's lead to the misuse of penicillin and the resistance will come. So when he discovered, he understood it was following resistance. Why? Because in nature, it was already there. So the fungi is every time trying to kill the bacteria. But did that make the bacteria extinct? No. So it's very clear that how much ever you try to kill them, they are evolving because of resistance. So he understood it in 1928, which unfortunately we are still unable to understand. When he discovered, he understood this is what is going to happen. But we are still struggling to figure out why that is happening, and we are misusing it again and again. So I'll see, all these infections are caused by the bacteria, and I will show you the bacteria like us. I can be alone here and I can be a part of a house, or I can be a part of a community. So they can be staying alone and they can be in a community. And as like humans in a community, they are stronger, much stronger. Okay. So here you can see when they are alone, they are resistant still. But when they form a community, they are called biofilms. And this community is thousands of folds time more resistant than the individual ones. And it's extremely difficult to penetrate this slimy material which you can see on top of the bacteria that protects it. So if you are adding an antibiotic also, the antibiotic is never going to even enter the biofilm. So the bacteria inside that is perfectly fine. So alone or in groups, they can be resistant, and they are much more resistant when they are in the group. Like if you are alone, you might not speak out, but when you are in a group, you speak out, right? Because you have the strength. It's the same thing they also do. So biofilms, I'll show you some biofilms. This is from my own lab. We produced it in Atria here. This is my PhD student's work. So this is a fungi. You can see this is a biofilm formed by a fungi. And this is a biofilm. You can see a slimy thing, right? It is forming the that slimy material for forming the biofilm. And down, if you see here, this is a dual biofilm, which means it is formed by this fungi and this bacteria. So if you think about what Alexander Fleming has said, the fungi used to produce antibiotics, right? That kills the bacteria. And what we did is, we even produced even more potent ones than penicillin, right? We made it potent. So what did they do? They found more partners to make them better. So instead of just sticking with being in a bacterial community, they found their partners who are more evolved than them. They found a fungi where they can grow better. So you are dealing with things which are even more notorious than when they are alone. So they understood that we are becoming potent. So they have to become more. And it's even from the figure, it's very clear. You can see how potent this will look like, how to break this kind of a barrier when individually their barrier is not that strong. So they are evolving much faster than what we are thinking even. Now I'll show you one more figure. Very ugly. But this is when your wound is infected. This is your lungs when it is infected. I just wanted to put some ugly figures to make you feel that how dirty it will look when you get an infection, because everything looks very beautiful in slides, right? It does not in your own body. So you should understand this is what will happen to you if you are not fighting something. So you know if AMR is coming and growing, You will probably at one point, I will probably one time will look like this, which is very ugly. So till now I have talked about antimicrobial resistance and how it is evolving, right? So now I would like to talk about what are the mechanisms which makes them resistant. Don't go with the figures because it may look complicated, but that's not it is. So how there are different mechanisms using which they will become resistant. And the first one is the bouncers. So if you get into a party, you are uninvited, you somehow get into the party, the bouncers will throw you out, right? So the antibiotics is also like that. So they get into the bacteria and bacteria like, oh, this is uninvited guest. I don't want them inside me. The bouncers will act. Those are called efflux pumps. They will push them out from the bacteria to the outside. Okay. So by that, they'll become resistant. Now comes the shield. So if you actually stop them even from entering your house, that's even better, right? So like us, we have pores in our skin, like that bacteria also has got. So that's the way all these things get into the bacteria. So what they have done over the course of time is they have evolved. They have evolved and they have blocked many of their pores so that less of antibiotic can in the first place enter. So that antibiotic cannot kill it. So that's the second mechanism. Third are the chemists. So when you, by the name itself, they are the bright guys. Okay, so they are not going to hide. They will fight you back. So that's the time when you have an antibiotic and the bacteria is like, no, I'm not going to hide or I'm not going to push you out, but I am going to bravely fight you and push you out. That is what the next step they will be trying to do. So here what happens is, for example, you are taking penicillin. Penicillin is going to get inside the bacteria and bacteria will have some chemists that will cut the penicillin. So they are going to chop the penicillin or they are going to modify the penicillin in a way that it is not usable. So again, the bacteria has gained resistance. Now comes the chameleons. We know the chameleons, right? If they want to catch a prey or if they want to escape from their prey, they will camouflage as per their surroundings, right? So here, what will happen is the bacteria knows that the antibiotic is coming. So what it will do, every antibiotic once it gets into the system, it will have a target, right? Like if I take cyanide, I will die because it has got a target which goes and kills me. Similarly, every antibiotic also has got a target. So this target, it will camouflage. So the antibiotic has actually walked into the bacteria and it cannot find the target. It's like, where is my target? What am I supposed to do now? Because I have got into the system, but I don't know because I do not have any other target. So that is what happening. So again, the antibiotic has become useless and the bacteria has become resistant. Then comes the detour. So in some cases, because we have produced extremely potent antibiotics. So all these barriers it will cross and it will get into the bacteria. So in that case, what will happen? It will find the target and it will kill. For some generations, it will keep on doing that. It will keep on killing the bacteria. But then the bacteria will start thinking, okay, this is killing me. I have to find a mechanism by which I can survive. So it will take the plan B. It's like plan B is I am going to die, planning. So I need a plan B. So what it will do is it will chart another metabolic pathway through which it can produce energy. So basically your antibiotic is coming and trying to kill you, but you have a different mechanism through which you are surviving or you are producing the energy. So that way again you are becoming resistant. But in this case, at least some of them will die for some time. That's when the bacteria will understand, okay, this is very highly potent and I have to be careful about this antibiotic. So now we know these are the mechanisms by which they are becoming resistant. So till now we have talked about what is their evolution, how they have grown bigger. So now I will talk how we are becoming bigger. Okay, so what is our part, what we will do. These are the different approaches now what we are trying to incorporate so that we can kill these bacteria. The first one, I'll talk about the biofilm. So we all know about the divide and rule policy of British, right? Which they have used on us. So we are here going to use the disrupt and invade policy, which is very similar to the divide and rule they have used on us. So it's like we are going to disrupt the biofilm, because until and unless something gets into the biofilm, it can never kill the bacteria. So first and foremost, rather than trying to kill it, you have to disperse it. Together, they are very, very strong, and they build biofilm fortress which you are unable to break at all. So here, what the researchers have done is, they have identified what are these extracellular slimy things that they produce. Most of them have got polysaccharides, proteins, DNA, lipid, all these things together makes the slime. And it's very thick. So what they have done now is, we designed some nanoparticles which will have some properties that helps them to go and attach to the slime, somehow break open that and get into the bacteria. So you are opening up the path, and you will have some drug attached to the nanoparticle which will go and act to the bacteria which is inside the biofilm. So that is one. Second is, you will have enzymes which can actually directly go and break the extracellular matrix. That is the slimy material. Even you have enzymes, you can have organic molecules, you can have synthetic molecules, you can design molecules which can do this kind of activity. Once it is broken, they are vulnerable. Now you can attack, because first you break, then you can even use the normal antibiotics which you are using, because the bacteria will die because of that. They are not dying is because they are forming the biofilm. So this is the first and one of the currently highly used strategy for AMR. Next is phage. I think during COVID time, this kind of pictures even came in Hindu or Indian Express. These are the viruses. Naturally, they looks like this. So usually we do not like viruses. They are bad. So this, I am going to talk about some good viruses which will not attack us, but it will attack only the bacteria. So those are the viruses which are very specific to the bacteria, and they will kill only bacteria. So what is the use of it here is, you can switch to a mechanism where there is no antibiotic. You are switching into something completely different. You are removing the usage of antibiotic from the whole equation. So no antibiotics, and you are going to use these phages. So what does this virus do? Virus always have the same kind of mechanism, be it us or it's a bacteria. So what they do is, they'll go and sit on top, similarly kind of attached to the bacteria, and they will release their genetic material inside the bacteria. The moment they do that, they hijack the control of the bacteria. Then it is under the control of the virus. It will decide what needs to be synthesized, and it will tell the bacteria to synthesize more of itself, and it will stop the synthesis of the bacteria. And at one stage, it will break open the bacteria, killing it and come out. But the plus here is, even if it's coming out, multiplying within us, it will not kill us, because for virus, they are very specific with the targets. We have even heard of viruses that infect only birds, or it infects only animals. It does not affect us. The ones which affect us may not infect the bacteria. So this is one technology where people try to isolate those phages which actually can kill the bacteria. And currently there are few of these. For example, biophage, this targets some specific set of bacteria which is more often on skin infections. And another set which is intestifage, which actually can target almost 23 different bacteria, including Salmonella and Shigella. We always hear about people eating shawarma, getting food poisoning. All these are from bacteria. So they're very dangerous, because most of the people, once they get that food poisoning, they die immediately. In shawarma cases, I think at least in Kerala, I have heard so many cases where people eat that and die. So that strong ones even can be targeted by the phages. Now, again, another non-antibiotic approach. So it's called the physical therapies. So can you guys think of a place where somebody is mechanically disrupting a biofilm within our body?
Skin.
Your teeth. When you have any, you remove the plaque that's full of biofilm. Your mouth has got a huge set of bacteria. It's always present. That's why sometimes you wake up in the morning, you have a bad smell. It's because of the bacteria inside there. That's why doctors say you have to brush before you eat, because it's bacteria you have to clean. Even if you're cleaning your teeth at night, still you have to do it in the morning before you eat food, because you have a full set of oral bacteria present. So when a dentist is removing that plaque, he is actually mechanically disrupting the biofilm and removing that. That's the most common form of biofilm mechanical removal. Then photodynamic inactivation. I think everybody knows UV has that capability. Even sunlight has, right? So when something is infected, if a soil is infected, you just put it out on sunlight. Why? Because of the light. Light can inactivate the germs. It could be bacteria, virus, whatever it is. So, but there are evolved technologies where you can use a specific wavelength of light. It could be green light, it could be red light, it could be a visible range. So what you do is you can use them as drug delivery molecules, which will be activated by light. So once it is activated, it can then kill the bacteria. And in such conditions, you can control it, because it's within your control how much you want to release. If I want to, if I'm only shining the light for 10 minutes, the molecule is going to release only that much. If I do that for 2 minutes, that much, half an hour, that much. So you can control how much of antibiotics or antibacterials you are releasing in this case. Then comes thermal effect. Heat will definitely kill, until and unless it is a bacteria from hot spring. It is going to kill the bacteria. So even with light to an extent will create temperature, and that can also kill the bacteria. So in this technique, one benefit is you are going to dismantle the biofilm first with physical methods, and then you can see whatever antibiotics you want, or maybe by mechanical removal itself you can get rid of that. If you're removing the plaque from your teeth, it's gone. You may have to slightly take some kind of a medicine to make sure your inflammation is coming down. Beyond that, probably you don't need anything. Now coming to microbiome recolonization. So I have talked about the good microbes in our gut, right? Those are the microbes which actually decides even what is your mood. They have a direct connection to your brain. So if I'm happy, maybe it's because my microbes are happy. If you are depressed, it could be because your microbes are depressed. They are unhappy because of the food you ate. So that's why we say you should have a healthy food habit, or you should eat or focus more on probiotics so that your bacteria can grow better. So there are situations, a lot of people these days talk about they are having stomach problem, acidities, ulcers. It's very common these days. And there are some infections that keeps on coming. This is caused by this bacteria, which actually one time if you get the infection, it's okay. But if it's recurring, then it's a huge problem. Then you will never be able to even eat anything properly. Such cases, currently what the scientific community is doing is fecal microbiota transplantation. So what you do is you will take the stool from a healthy person and you will transplant that to the sick person, so that the microbiome from there can grow and flourish in your system. That is a very tricky thing to do the first place. So now what they are doing is the research is focusing towards forming microbial consortia from the stool, or you can identify the best ones, you can have a mix of them, and you can feed the sick person that, so that his microbiome will flourish from that microbial consortia. So that is where the future of this research is going. Now coming to integrated multi-omics. Here, this I will not say this is a technique which will give you a direct output. It's an indirect output. So when I said a bacteria is alone and when a bacteria is in a group, they are different. So like when we are alone, at home we will have a different personality. When you are here, you are like, all sophisticated. That's not what you or we all are inside home, right? That's the same way when they are alone also, bacteria is like that. But when they are in a group, they are different. So they have a completely different way of behaving, communication. They produce a different metabolite. They produce everything differently when they are in the biofilm. So it's very important that when you are in a normal condition, when you are not sick, how your system is working. It's very important to know the base level. Then you need to know in an infection how you are, or what changes are happening. Maybe your gene regulation is changed, your protein production is changed, the metabolites that the bacteria synthesis has changed, everything. Pretty much everything changes, and even at different stages of infection it changes. The beginning stages it may be different, after 2 days of infection it is different, after 4 days of infection it is different, so you don't know. That kind of a data at this moment is not available. See, because if you can do that, you can most probably identify some biomarkers which can help you to deal with this problem holistically. Right? You can identify in this disease, okay, I am getting a pneumonia. The third stage, this is third day of the biofilm infection. This will be the metabolite. This will be the gene regulation. Then you can probably target something very specific, and you do not have to go for broad spectrum antibiotics. You can mostly kind of have a personalized thing, at least to a level where it is personalized to the bacteria, even if it's not for us. Now the next will be A. So A powered drug discovery for antimicrobial resistance. So I think this is an example everybody caught. When if you want to have a new discovery, especially in antibiotics, it's very difficult. And pretty much I think the pharma companies have stopped investing in antibiotics is because in another 5 years it is going to become resistant and they will never get their ROI. Why should they invest when they are sure that they are not going to get their returns back? So the pharma company now don't want to invest, and actually we do not even have a future pipeline which will give you more antibiotics. So we are actually stuck because we have to deal with whatever we have. Nobody is going to discover or identify more and more antibiotics. So there comes the use of AI. So traditionally, if I want to discover something, maximum I can take is 100 compounds. Then you will have to take it through a high throughput analysis in the lab, identify, bring it down to 10, and probably then go for in vivo studies. That's the maximum I can do humanly. But here the AI models can help you, where probably millions and billions of molecules can be checked through in a library. Then you can bring it down to 100 or bring it down to 10, where you can take it to the, so you are reducing the cost hugely and you are covering a huge spectrum, which nobody probably will again have to check. So for example, in such cases, you can see these are AI discovered, very recent antimicrobials from 23, 24 and 25, which is found to be highly potent to the bacterial pathogens. So Stanford was doing a research which is for AI-based drug discovery. Sounds very similar to Symbio AI, Synthemol. So what they have done is they have gone through almost 30 billion molecules and brought it down to 58. Then further brought it down to 6, which are very different or novel molecules which shows potent antibacterial activity against the escape pathogens. So they are very relevant. From there, now you will have to go for in vitro, in vivo, and then clinical studies. Then only it will come to the market, and that's why the pharma company is not happy to invest, because even if you identify a molecule, it will have to go through even the clinical trials, where at any stage something can go wrong and you cannot bring it to the market. And also studies are going on in AlphaFold. Okay, they are trying to make a successor for AlphaFold, where you can have better predictions for the structures, because even now there are a lot of proteins which does not have a structure. If you do not have a structure, how will you, what is the base? You give a sequence, how will it know that that should be the structure of the protein? You don't know. So that kind of data still is not available. So they are trying to have add-ons where the AlphaFold can be made better. So with this slide, I will say we are, like I said, we are stuck here basically. So that is what we have to understand. We are stuck here, and probably there is no one single best method to combat this issue. It's about how best you can use all the available methods. That's the only way you are going to fight this issue. So a little bit on my research here at Atria. I work primarily on AMR and three major pillars of my research. First one is I'm so fascinated with the bouncers since very long time that it's efflux pump, how they work. That's something because they are so diverse. They can detect single pump can detect structurally diverse molecules. How they do that is something nobody. The studies are happening in efflux pump from several decades. Nobody was able to identify why it's like that. It can detect a molecule this small and it can detect a molecule this big. How the same pump is doing the same thing. And it is adjusting itself to identify all these things. And the next one is biofilm. Like you have seen the figures, we are developing biofilms. And that too mostly not the monospecies one, dual ones, where they are much stronger. So that you, whatever work you do, it will have some kind of translation or it can have some clinical relevance. Because now there is no point in you working with just a bacterial biofilm or just a fungal biofilm. That's not what you see in real world. If you have a pneumonia infection, we say that it's caused by Pseudomonas, right? But it's not just Pseudomonas. You may have a Klebsiella there, you may have a Bacillus in there, there'll be even fungus, we don't know. Because primarily it is caused by a Pseudomonas. There could be 100 other pathogens sitting along with that. So we are always in real life dealing with multi-species biofilms. So here in my lab, I am trying to develop those study models where you can use these methods. And as you study these two mechanisms, it's inevitable that you have to identify some strategies to block them. You are studying the mechanism is so that you can have an application for that mechanism. So here we are also trying to develop techniques by which I can disperse the biofilm and try to eradicate that infection. Hope I didn't bore. Questions?
I have a question about using the combination of techniques to solve AMR by identifying the biofilm. Is it different from species to species? For example, the way you will handle the plants, is it different from how you will handle the animals versus humans? Which of these strategies is more likely to succeed? Does the answer depend on the species in which the bacteria is present?
Yeah, definitely.
It's different.
Mostly if you find something for the human, I think pretty much for animals it's sort of okay. But with plants it will be completely different.
I see. And bulk of the research around the world is focused on
Yeah.
humans, is that correct?
Yeah. Because ideally we are interested in only us. So I think agriculture, not too much research is happening, even though we are flooding it with the antibiotics. The biofilms are. Yes, it is, because anything you add to the plants are going to the water system, which ultimately comes to us. So that's there. Huh? Yeah, animals, because veterinary nobody even take care. If there is like we use even antibiotics in chicken so that they gain weight. It's nothing to do with its antibiotic property, but it's for growth stimulator that you do with agriculture also. So you are actually feeding both. Maybe we are a bit cautious on ourselves, but with animals and plants, yeah.
Where are we in terms of research when it comes to individual centric?
Like each person. I think we have to travel leaps and bounds till we reach that point, because data is there, but I have, see, we all are different, right? So much different. It's just that at least if we have the basic data for each and every antibiotic, from there we can build. But that even is not currently available. So if I say one dose is for penicillin, for other thing I don't know. We are just following a norm, which is not the proper way. You have to find that exactly, at least with research. And when we talk about personalized, ethnicity will come. Maybe for a Western person it's different, for us it's different. People say that we even have genes which can metabolize starch much better than the Western people. That's why our, actually even we are still very diabetic because of the huge amount we are consuming, but we are actually metabolically much better than them in consuming the starch. So similarly, if maybe I am doing a study, its effect on me and a person who is a British or a US person is completely going to be different. So personalized is, I will not say, not in the near future. Yeah.
So all the techniques that you described, right? There were some which where you're saying you want to understand the mechanism. Right? I understand that science part of it, but then you also need a mechanism to either trigger or inhibit that mechanism. Is that trigger always going to be drugs?
No.
What else is
Toxins. Any toxins.
As in you're proposing injecting toxins.
See, but all these bacteria, they are present in soil also.
Right.
So there, if there is like a fungi is there, it will try to kill it. So whatever it producing, or maybe it's a metal ion that's coming, it's toxic for it. So anything toxic, it will identify. Mostly if you take even influx it only detects, it's never detecting antibiotic, it's detecting that it's a foreign molecule.
I understand, but what is the intervention that can be done to simulate efflux pumps to get better or being able to penetrate them? What is is the intervention always drug based? Is the intervention always drug based?
Usually studies are drug based, but there are interventions also. There are at least few inhibitors that's been designed, even one from IIT Roorkee, where they have designed an inhibitor, a small peptide which can block efflux pump. But they have to be, when you are dealing with something like this, like personalized medicine, they have to be very specific. Otherwise, I don't know what it is going to inhibit. I also have the same pumps, it can inhibit me.
Any questions from online?
Yeah.
So you discussed microbiome and so I remember at least 10 or 12 years back this was a very big thing, healthy gut versus disease gut, and there was a lot of promise. Does anything has anything translated actually? Or?
Now it's mostly fecal transplantation happening. But yes, studies are progressing where you can make that combination. See, because when you make a combination, like I said, if I'm taking that combination, maybe it will not flourish in my gut. I don't know. Maybe my combination is pretty much a lot personalized, because it's depending on each and every person's gut. So that's why that research is, even if it's progressing very slowly.
Okay, if there are no more questions, let's thank Asha
Thank
and
you.
also for finishing right on time.